we have been discussing digital modulation techniques. So far we have discussed what are the different digital modulation techniques which are used in practice: PAM, QAM, PSK, FSK, PPM, all these techniques we have discussed. Also we have classified digital modulation schemes and discussed different types of modulation schemes like orthogonal modulation, bi-orthogonal modulation, then simplex signal set. And then we have discussed different type of receiver structures. For first we have discussed also different generic receiver structures for any given signal set: matched filter receiver, correlation receiver. We have discussed matched filter in detail. We have shown that it is optimum. We have shown that sampling at multiples of capital T seconds is optimal. And in the last class we have discussed eye diagrams, which is a way of seeing how much ISI is there on the oscilloscope. Then we have discussed mapper in detail, and we have seen that by using gray coding we can achieve probability of bit errors almost equal to probability of symbol errors for many modulation schemes, because most of the times the symbol errors happen because of detection of neighboring points of the transmitted point. So the gray coding ensures difference of only one bit between neighboring points, and thus most of the symbol errors will result in only one bit error with gray coding. In this class we will and then also in the last class we have seen the relevance of discrete memoryless AMRE channel and also real vector channel discrete time, even for continuous time channels, even for communication systems with continuous time channel. In this class we will start probability of error calculation for different kind of signal sets. Whenever it is not easily possible to compute the probability of error, we will also see ways of finding an upper bound of the probability of error. Upper bound of probability of error will also be useful, because then we can guarantee that the probability of error for the system we are designing will be less than so much, say less than 10 to the power minus 5. So that is nice. So lower bound does not make sense, it is not useful. Upper bound of the probability of error is useful. So if you say probability of error is greater than 10 to the power minus 5, then it can be even 0.1, it can be 0.2. So anything greater than 10 to the power minus 5. So that is not useful. But if you have an upper bound, if you say that it is less than 10 to the power minus 5, then that is nice, because we know that out of 10 to the power 5 bits, about 1 bit will go wrong. So for this class and for the next class we will discuss probability of error calculation, and for this topic I will advise you to read out of these two books, Prokis Digital Communication and Ozencraft and Jacob. I will specially recommend this book for this topic, especially for the systematic treatment for generic receiver structure, and also the discussion of signal set in terms of vector spaces in a very systematic manner. Please read this book. And also probability of error calculation, which we are going to do for this in this class and the next class. This book will be very nice. And in fact, the approach of vector space approach for signal design was introduced for the first time in this book. So, it is a very classic book on this topic. So, Digital Communication by Ozencraft and Jacobs. Okay. So, let us see how we can compute the probability of error for different signal sets. So, we have seen that a generic matched filter receiver structure is this. Probability of error will certainly depend on how we do the detection. So, we have to keep the detection in mind, how we have implemented the receiver to compute the probability of error. If we do the detection in the not optimum way, then obviously the probability of error will go up. So, we are going to analyze the probability of error which is minimum, that is the best receiver structures will give that probability of error. So, matched filter is an optimum, matched filter receiver is an optimum receiver. So, we are going to analyze this receiver. So, here we have seen that the channel output YT is fed to two matched a bank of matched filters matched to the basis signals, orthonormal basis signals. So, we will sample at capital T for the first symbol and then again at multiples of t. So, at these instances this is YT and then we have this weighting matrix . This basically computes j equal to 0 to n minus 1 yj x mj for the mth output. So, here we have and out of this we will select the largest. Which will give us the estimate of m. This is the receiver structure. Now, channel is assumed to be ideal AWGN channel which adds only noise. This is the receiver structure for generic signal set, n dimensional signal set. Now, we will assume, as we have done before, that NT is white Gaussian noise with mean 0 and variance n naught by 2. Why it is written in this form? Because it is the variance of the noise with power spectral density n naught by 2. If you draw the power spectral density of the noise, it will look like this with n naught by 2. And what is the these are the yi's, y1, y2 and so on. y0, y1, ym minus n minus 1, now we will see what is yi. We have seen it before already. So, what is yi? Yi is the output of the filter at capital T, and it can be written as yt phi I t dt. And this is equal to x t phi I t, where y t is x t plus n t plus n t phi I t dt. We have also seen before that this part, this block is equivalent to finding the distance of compute distance of the vector y with different x m vectors, the signal vectors, and take m hat for minimum d. So, that is, we originally actually had this as the receiver structure. Then we have seen that computing the distance and finding the minimum distance, that is the picking up the minimum, the nearest signal point from this vector y is equivalent to performing these operations. So, to find the probability of error, we can assume that we are doing this, because the result will be same. So, this is x m I, suppose x m was transmitted, then we will have m here, then x m I, ith component when we do this, plus this will be the noise. In fact, we have seen before that if we take an orthonormal basis and take a signal in that space, then you can compute the component, ith component of this vector or signal by simply taking the inner product of x m with phi I. Now, we have this. Now, this is the one ith component that was transmitted, but this is a noise which has corrupted this. Now, we need to characterize, we need to find out what is the distribution of Ni to know the probability of error. So, we need to know how often this will corrupt it so much that these noise components Ni's, n naught to n capital N minus 1 components will corrupt the received vector, the transmitted vector x so much that we will detect wrongly. So, to do that, let us see what Ni, what kind of noise Ni is, what kind of random variable Ni is. So, this let us see phi I t first of all we know that is orthonormal, and so that is it's not so it is unit energy we know. So, phi I t minus t is also unit energy, because it is nothing but flipped version of phi I t. So, this is unit energy, and Ni is the output of this filter with this impulse response. When the input is when excited by Nt. So, you can see here that Nt is the inner product, Ni is the inner product of Nt and phi It. So, it will be the output of the filter with impulse response phi I capital T minus t when the input is Nt. This is also the convolution of Nt with phi I capital T minus t at capital T time. So, Ni is the output of the filter. So, that is this filter is there phi It minus t, there is Yt, this is Nt, and this output at capital T is Ni. We have seen it here also. So, because this is Yt is xt plus Nt. So, Nt part it goes through here, and at capital T it is the Ni component. So, this is the filter with unit energy impulse response. Nt is white Gaussian noise with 0 mean and variance n naught by 2. So, we need to characterize what is Ni, what is the distribution of Ni, what is the mean of Ni, what is the variance of Ni. First of all, Ni is known that it is known that if Nt is white Gaussian noise, if it is Gaussian, Ni is also Gaussian. So, first of all Ni is Gaussian. Okay. And because Nt is 0 mean, Ni is also 0 mean. And variance will compute, but before not only compute variance, we will compute the covariance between any two of these noise components n naught to n capital N minus 1. If you take any two noise components, we will compute the covariance between them. So, that will give us variance of Ni if we take covariance of Ni with itself, and covariance of different noise component pairs also. So, let us compute the covariance. What is covariance? Covariance of Ni and Nj, I and j may be same or different, is we know that covariance of two random variables is given by this, because these are 0 mean, we need not subtract the means. This is 0 to t Nt phi It dt, 0 to t n tau phi j tau d tau. We are just taking two different variables in those two integrals, because we are going to combine these two integrals into one double integral. So, this is expectation of 0 to t Nt n tau phi I t phi j tau dt d tau, expectation of this whole thing. Now, we can take the expectation inside, and these are fixed functions. So, we don't, this can be taken outside the expectation. We have inside the expectation only n t and n tau phi I t phi j tau dt d tau. Now, what is the expectation of n t and n tau? product. This is the autocorrelation function of a white Gaussian noise at t minus tau. So, because it is white with power spectral density n naught by 2, we know that this result is nothing but n naught by 2 delta t minus tau, and phi I t phi j tau dt d tau. Now, let us write this in a little different way. We take the t part separately outside, phi I t, this is independent of tau, and then do the integration on tau. N naught by 2 is constant, so n naught by 2 outside, then delta t minus tau phi j tau d tau dt. Now, this is equal to n naught by 2 0 to t phi I t. Now, what is this integration? This is a delta function shifted by t, flipped and shifted by shift. Flipped version is same. Delta t minus tau is same as delta tau minus t. So, delta tau minus t times phi j tau integrated. So, it will be nothing but phi j of t, this whole integration. That is the way, in fact, that is a part of the definition of the delta function. This is delta j t dt, and this is equal to n naught by 2. And what is this integration? We know that these functions are orthonormal. So, if I is equal to j, this integration is 1. If they are not equal, then the integration is 0. So, in other words, this is the Kronecker delta. If I is equal to j, this delta is 1. If I is not equal to j, this delta is 0. This is called the Kronecker delta function. This is different for Dirac delta function. Well, Dirac delta is not a function first of all, but anyway, we loosely call them function. Delta, this delta is Dirac delta, which is continuous, whereas this delta is discrete. For it is valid only on discrete values of I and j. So, this is the thing. So, what is the variance of n I? For any I, it is expectation n I square, and that means n I times I, that is I equal to j. So, for I equal to j, it is 1. So, it is n naught by 2. So, this is the variance, and covariance of n I and n j for I not equal to j is 0. So, that means these noise components are uncorrelated, and we already know that they are Gaussian. So, if you have two Gaussian random variables, they are uncorrelated, then we also know that they are independent, because we know the joint distribution of two Gaussian random variables. There is some correlation coefficient which comes in the distribution. If we make that 0, we can see that it can be the whole distribution probability density, joint density can be broken into two parts, a product of two different densities. So, it is the density of n I times density of n j. So, they are independent if they are uncorrelated. It is not true for any other distributions, not all distributions, but for Gaussian it is true. So, here we have seen that the noise components that we are getting n naught to n capital N minus 1 as part of this vector y naught to y capital N minus 1 are independent, Gaussian with variance 0 mean and variance n naught by 2. Okay. So, now what is the noise doing to the points we are transmitting? Suppose we are transmitting a vector x, xm, and we are receiving y. It will not be exactly xm, but it will be somewhere else. Where will it be? That depends on the noise vector. So, if this is the point xm we are transmitting, we have transmitted, we will receive somewhere probably here, which is the received vector y, and this vector is xm plus the noise vector, that is n naught n1. We are considering two dimensional, so n naught n1. So, n naught will be added to the x1, the first component x naught, then the second component will be added with n1. So, if this is the receive point, then from here to here this vector is n naught. Similarly, this vector is n1, this much, and this is n naught. So, this is the receive point, this is the transmitted point. So, noise deflects, the noise vector deflects the transmitted vectors. So, this way, if we take the, if we transmit a sequence of symbols, symbol after symbol, every capital T seconds you transmit one symbol, and at the receiver you extract the vectors y for different symbols, and suppose you plot those points in the vector space. So, because we can plot nicely for two dimensional, we can plot for two dimensional vector spaces. Let us consider only two dimensional vector space for time being. So, suppose we plot all for every symbol, you extract that vector, you generate that vector using match filter and sampler, and then you plot that vector on the two dimensional plane. You do that for all symbols, you keep doing that. Then there will be more and more points. For every symbol you will have one point somewhere on the plane, and what will be the ultimate look of the plane plot? So, it will be something like this if you use 4 PSK. So, if you use 4 PSK, received points will be like this. Received vectors will be this. We will transmit either this or this or this or this, sometimes this, sometimes this, sometimes this, or sometimes this, these points. Now, when we transmit this point, the noise at different symbol interval will be different. So, noise here, sometimes it will be here, it will deflect the point to here, sometimes it will deflect the point to here, sometimes here, and so on. But because the noise is Gaussian, the probability that the noise is of smaller value is more. So, most of the times the noise value will be small. So, the received points, if you transmit only this point always, the received points will be, more points will be near this, then few more points, then again even fewer points further. So, as you go further, there will be less and less points. That is seen in this diagram, this plot. As you can see, as you go further from this point, the points are becoming less dense. Density of the points is decreasing. That is because the noise value is most of the time small. So, similarly, when you transmit these points, you will receive these points. They will be scattered towards this point, and similarly for these points. Now, it may happen that when you transmit this point, sometimes, very rarely, the points go very far from here and somewhere here, or somewhere here. Then we will make a decision error at the receiver, because this is nearer to this point and we will think that this was transmitted. So, there will be decision errors whenever the point goes very far. And when exactly will be the errors? Suppose we transmit this, then the decision region for this point we have discussed already before is this region, this part, this region. So, whenever the noise is so much that you transmitted this and you received somewhere outside this region, then there will be decision error. If it is on this side, you will think this was transmitted. If it is on this side, you will think this is transmitted. If it is on this side, you will think it is on this one was transmitted. So, there will be decision error if the received point is not in this region. Okay. So, the points will look like this. Now, we will start now computing probability of error for different modulation techniques. Let us compute first for the simplest modulation technique, that is PAM. So, probability of error for first binary PAM, the simplest. Binary PAM. So, we are transmitting, suppose we transmit these one of these 2 points, suppose this distance is d. So, this is basically x naught equal to d by 2 and x 1 is minus d by 2. We will receive somewhere here. If we transmit this, we will receive somewhere here nearby. If we transmit this, we will receive some point somewhere nearby. Now, what is the average probability of error? P average, average probability of error. Let us say PE average. This probability is, see, half of the times we assume that these 2 points are transmitted with equal frequency. Then half of the times this is transmitted, half of the time this is transmitted. Then the probability of error will be half times the probability of error when you transmit this and half times the probability of error when you transmit this, the average of the 2 probability of errors. So, half probability of error when you transmit this, that is, if you transmit x equal to x naught, that is d by 2, if you transmit d by 2 value, when will be the error? The error will be when the received vector is less than 0, it is negative, then you will detect this and as a result there will be error. So, the probability of error when this is transmitted is nothing but probability of y less than 0 when x is equal to d by 2. Y is equal to x plus noise, remember that, and plus half times the probability of error when this is transmitted. So, probability of error when x is minus d by 2, given x is minus d by 2. So, error will happen when y is greater than 0 for this case. So, y is greater than 0. Now, this is half p, as you said y is x plus n. So, y is less than 0 means x plus n is less than 0, but x is equal to d by 2 for this case. So, x plus n less than 0 given x equal to d by 2 plus half probability x plus n greater than 0 when x is minus d by 2. Now, if the x value is d by 2, when will this happen? X plus n is less than 0 when n is less than minus d by 2. X is d by 2, so you take d by 2 on this side, n less than minus d by 2. So, this is half probability n less than d minus d by 2. Then if x is minus d by 2, what is the probability of this? The probability of this is the probability of n being less greater than d by 2. Probability n greater than d by 2. Now, you can see the noise is n is Gaussian, it has one component n not only. So, we are denoting it by n itself. N probability of n has Gaussian distribution with 0 mean. So, the probability that n is greater than say this d by 2 or less than minus d by 2, that is the area here is probability of n greater than d by 2, area here is probability of n less than minus d by 2. This area is probability n greater than d by 2. Both are same because this is noise is symmetric. So, for symmetric noise, if you have such a symmetric signal set, probability of error for this will be same as probability of error for this, as you have seen here. This is same as this, so this will be same as this. Now, so we can write this as any of these, because half times this plus half times the same thing, this is same as this. So, this is probability of, we can write n greater than d by 2, only this term. So, now what is this? Now, this is difficult to actually compute in closed form. This is actually the integration of the probability density function. This is the integration of d by 2 to infinity 1 by root over 2 pi, then sig root over n naught by 2, then e to the power minus, so minus x square by 2 sigma square, that is n naught by 2 again, 2 cancels, 2 cancels, dx. So this is this probability, this is the area here. We are integrating this curve from here, d by 2 to infinity. So this needs to be computed, but there is no closed form computation for this, and there is a function defined which is implemented, which is there as subroutines in MATLAB, which is used very much, which will enable you to compute this kind of probability of errors. The function is as following. The function is called Q function. It is defined to be defined in the following way. Suppose Z is a random variable which is Gaussian, mean 0, variance 1. Such random variable is denoted by n, 0, 1. N for normal, you know that Gaussian distribution is also called normal distribution. So, n for normal, 0 mean, variance 1. So, variance n naught by 2, which we had for this n random variable, is denoted by n, 0, n naught by 2. The variance n naught by 2 mean 0. So, suppose we have a random variable this 0 mean 1, variance Gaussian, then Qx is denoted is defined to be root this x to infinity e to the power minus x square by 2 dx. Basically, the integration of this x to infinity p of z dz. So, if you plot the probability density function of z, Gaussian 0 mean, variance 1, take x anywhere, this area is called the Q. This is Pz, this is Q of x. Q of x is defined as the probability of unit variance 0 mean Gaussian random variable taking value greater than x. So, this can also be written as 1 minus the cumulative distribution function of z at x, that is 1 minus f of fz of x, the random variable z at x. Okay. So, this is Q function, and let us now see what we need to compute and try to express the Q function. So, Q function cannot be really computed in closed form. Numerically, the integration can be found, and routines for programs for finding this integration for different value of x is available in MATLAB. Not directly Q function, but some other function called ERFC, from which you can now derive Q function. So, please look at ERFC function in MATLAB and try to express Qx in terms of ERFC of x. So, ERFC function in MATLAB. Because later we will give I will give exercise to do in MATLAB, and there you will need this ERFC function. Okay. Now, we are trying to find out the probability of error for binary signal set, and we have come to this level. that it is probability n greater than d by 2, where n is a Gaussian random variable with 0 mean variance n naught by 2. Now, let us derive another random variable from n. That random variable z is n by root over n naught by 2. We are just scaling this random variable n by this scalar. Now, this is just scaling of a Gaussian random variable, so this is also Gaussian. Mean of n is 0, so 0 mean. Variance of n is n naught by 2, that is standard deviation of n is root over n naught by 2. So, the standard deviation of z will be standard deviation of n by this. So, it will be 1. So, variance is also 1. So, we have derived a random variable z from n, which is 0 mean Gaussian with variance 1, which was used to define the q function. Remember, so q function was defined with respect to density of such a random variable. So, now the integral we want to, the probability we want to find is probability n greater than d by 2. N is greater than d by 2 if and only if z is if n is greater than d by 2, z is greater than d by 2 by this. So, it is d by 2 by root over n naught by z is greater than this, that is p z is greater than d by root over 2 n naught. Okay. So, now this is of this form. The definition of q function, if you see, is that q of x is defined to be probability z greater than x. This is also probability z greater than x, that is q of x. So, here z is same random variable, that is 0 mean Gaussian with variance 1. So, probability of z greater than d by this is nothing but q of d by root over 2 n naught. So, this can be computed in MATLAB, or table for this also exists, q function table. So, you can find this value and then find out the value of q at that point. Okay. Now, now we have expressed this in terms of d, the distance between the points. This is d. Now, if we want to express in terms of the energy of the point, because we know that increasing the energy, energy is something real, you can compute energy, it is same as the energy of the signals. So, in terms of energy, can we express it? If we increase energy, we should be able to decrease the probability of error and vice versa. So, in terms of energy, we will express the probability of error, but that is very simple, because the energy of average energy E is nothing but energy of one point, because energy of both the points are same, because they are same distance from 0. The distance from 0 is same. So, this is d by 2 point and this is minus d by 2 point. The energy of both the points is d square by 4. So, d is 2 root e. So, here we can put in place of d 2 root e, and then q of 2 root e by root over 2 n naught, that is q of root over 2 e by n naught. So, we have expressed the probability of error for binary PIM in terms of the average energy that is transmitted and the noise power spectral density. Okay. Now, we will see some example, we will see some exercise. Exercise 1, I will advise that you please solve this exercise as soon as possible, because this will also make these ideas clear in your mind. There are for many more exercises in Ozencraft and Jacob, and I will encourage you to try to solve those problems, because then you will be able to understand the next class better. Okay, so, exercise 1 is prove that Qx is less than e to the power minus x square by 2. So, this is an upper bound of Qx, and using this upper bound you can get an upper bound of this probability, and such probabilities which we will compute later also, probability for different like QAM signals will also be expressed in terms of Q functions. Now, if we are not given MATLAB, if you do not want to do numerical integration, we can at least approximate Qx, we can upper bound Qx by this, and then we will get some closed form expression which will be the upper bound of the probability of error. So this is useful that way. Then exercise 2. Exercise 2 is using MATLAB. Please simulate a PAM communication system based on PAM using MATLAB. That is the exercise. The details I will work out now. First step is, so the idea is to, exercise is to simulate transmission or communication, transmission and reception, communication using PAM, rather binary PAM through AWGN, discrete time. So, remember the relevance of discrete time channel model in the context of continuous time channel. If you take the modulator block and the matched filter and sampler block at the receiver, together with the channel they form a discrete time channel, and I am not asking you to simulate the inside, just assume a discrete time channel. So, do not go into continuous time, just take the discrete time channel and simulate the outside blocks. I will now explain step by step what is to be done. First, the steps are, first generate the information you want to transmit, generate uniform, the distribution is uniform, discrete random process, discrete binary random process, because the values will be binary, meaning by, so binary, meaning by generate a sequence of bits, MIs randomly. So, MI is the ith bit, that is a message, one bit is one symbol, I equal to 0, 1 and so on till say 1000 or 1 lakh you can take. Then each MI, as I said, is from 0 and 1, that is it is a bit, value is either 0 or 1. Next step is do mapping of 0, 1 to some level map. So, you have MI, from there you construct another variable, another sequence of variables, that is a random process. If MI is 0 for any I, if the MI, the bit is 0, take xi equal to minus d by 2, if it is 1 take d by 2, that is the binary PAM mapping. Then we want to pass xi through the channel, discrete time channel, inside which all the modulation and matched filter, sampler, all these are there inside the channel. So, we will not simulate the channel, but we will simulate only the output, that as the whole channel as a black box. So, how do we generate the output of the channel? So, to generate that we have to generate the first the noise process. So, generate first, generate a white Gaussian noise, discrete time, white Gaussian noise Ni with mean 0, variance n naught by 2. So, once we have generated Ni, so you can generate using rand n function, use rand n in MATLAB. So, using this function you can generate a sequence of random numbers with distribution Gaussian distribution mean 0, variance n naught by 2. So, once you generate that, you already have the sequence xi, x naught, x1 and so on till x say 1 lakh. So, you add for each I add xi with ni, and that is your yi, that is the received vector xi plus ni. So, you will get y naught, y1 and so on, that you have got by adding the noise sequence to the transmitted sequence. Then at the receiver, what do we do? The fourth step is the detection. Detection means detecting which value was transmitted, which value of xi was transmitted from yi. So, if you have now the mapping, the detection will be, we know that for binary PM, this is the estimate of xi hat. If it is greater, if yi is greater than 0, take it to be d by 2. If it is less than 0, take it to be minus d by 2. And then you can subsequently do demapping from here. For yi greater than 0, xi hat is d by 2 and mi is 1. For minus d by 2, that is less than 0, yi is 0. So, you have got mi hat, this is not mi hat, this is the estimate of mi hat at the receiver, this is the mi hat. Now, count, you have the sequence mi, I equal to 0, 1 and so on, you have the estimated sequence mi hat at the receiver for I equal to 0, 1 and so on. See the difference between these two sequences, see how many bits are different in those two sequences. So, count how many bits are different in mi and mi hat. If total if say say L number of bits are different, that is, if L number of bits were received wrongly out of say capital L bits, out of capital L bits are received wrongly. So, the bit error rate also called BER in short in most of the literature, BER is L by capital L. This is the estimate. If you should take sufficiently large capital L to get a fair estimate of the bit error rate, and bit error rate you should compare with the probability of error, that they should be ideally same, but they should be very near for large capital L. If you take capital L equal to 10 to the power 10, you will have almost same, the bit error rate will be same as the probability of error you have computed using the formula, using Q function. So, compute probability of error and verify with BER. They should be almost same. Next step of the exercise is to simulate the continuous time channel itself. Take xi, modulate it with a pulse pt, and then receive pt and pass it through match filter, and then get yit instead of just generating a noise sequence, discrete noise sequence, and adding with xi to get yi. You implement the inside of the thing also, inside of the discrete channel also, in terms of the continuous time channel. So that also can be done. So that is the next step. Sixth, do not do yi equal to xi plus ni, but take continuous time channel, that is now nt. This is the channel. Here you will have modulation. This is xi. It is multiplied by pulse pt. Pt you should take unit energy to verify with your probability of error. This you should take unit energy Pt. Then pass it through matched filter and then sample at capital T or multiples of capital T and then get yi. So previously you just did this as a black box. Now implement these also. So this way you will be able to verify whether the formula using which you are computing the probability of error in MATLAB will actually, whether it gives you the correct an impression of how many bits will go wrong in practice if you use that modulation scheme and that kind of receiver system. So in the next class we will continue discussion on probability of error for other modulation techniques, and whenever not possible to compute the probability of error easily, we will try to see if we can get an upper bound on the probability of error in an easy manner. See you in the next class. Thank you.